everyone, I'm Claire, and today let's talk about how to prove the very famous and useful theorem, and this is the famous little theorem, and we're going to prove the stronger theorem. It's stronger theorem, and this is all torsion theorem. And of course, the problem comes from, first I met a problem, and this problem is A over B, and it's congruent K mod N. And so what is the value of K? And so what this problem actually means, I will talk about it at the next video. So let's see. First I met this problem, and if I want to calculate K, and then I just both sides times B. So I have A congruent B times K. So, and then it's mod N. Okay, great. So now next step, let's see, okay, here. So B times K here. So A is congruent to B times K mod N. So the problem is, what is the K? It's still, and the problem is always K. What is number K? Here, right? So how do I find it? You see here. So when you find a multiple, when you want to find what is value K, so B to the K minus a multiple of N, I just say N Y maybe, and then that's equal to A, right? So that's the point here. So, and using the Bezier equation. Okay, using the Bezier equation. So what we have here, if we use the Bezier equation here, so we have, so we can, first we calculate BK minus NY equals their greatest common divisor. Of course, in the problem I met, B and N need to be co-prime. So it is equal to 1 because you don't know what a number A is. Because sometimes A maybe is not the multiple of B and N's greatest common divisor. Okay, of course I don't talk about here, okay? And I'll talk about it in the next video. Okay, just like this. Okay, the condition is B and N are co-prime, so it's equal to 1. So, okay. So, ready, if we have it, so actually we actually don't need to use the extended Euclid algorithm to find what's the number K. Actually, we'll prove it later. We can use all the torsion theorem to have it. Of course, here, you see. So B is, I just made a problem and right on the step, and we have B to the negative 1, and that's congruent B to the 5 of N, and then B to the 5 of N minus 1, and that's mod what? Mod thing here. It's mod N. Okay. So this is a problem here. So I just think, what is that doing here? So, and you see, of course here, B to the negative 1, and this is not just a 1 over B, it is a modular inverse, okay? And I want to calculate a modular inverse, and this B to the negative 1, this modular inverse is the modular inverse of B to N. So if I want to calculate B to the negative 1, we can still also use this Bezier equation. Only this Bezier equation. So K and B to the negative 1 is just one root of K, right? And so that's the point, because K, when we find a number K1, so K is equal to K1 plus Tn, because it should be T times N over greatest common divisor of B and N, but greatest common divisor of B and N, because B and N are co-prime, so their greatest common divisor is equal to 1. So it's just plus Tn. So that's the point. So that's right. So if this is a root of K, so this number must be also a root of K, right? So because the difference is multiple of N. And if both of them are a root, only could be both of them are case roots, because only that happens. So that means their difference is a multiple of n, right? So this one must be a root. And so let's see here. So that means if I put it in here, so it is bk, and b times b to the 5n minus 1, so it is just b to the 5n, right? What's that equal to? Not equal to. So then the minus a multiple of n, I can say a multiple j multiple of n. And that's a good one. So easy here. I can change this place. So b to the 5n, and j need to be integer. Minus 1 and a n is equal to nj, and j is the integer. So b to the 5n minus 1. N. So n is the divisor of b to the 5n minus 1, right? So, and if we move that, we can change it to b to the 5n congruent to 1 mod n. And at first I don't know. Actually, this is just the all at certain theorem. So, and at first I thought. That's my thought, okay? I just think if I can prove the Fermat's little theorem, and I can prove all torsion theorem. Let's see what I think, okay? But actually, I can't. I only prove a part of all torsion theorem if I prove Fermat's little theorem. First, let's see. B to the 5n, because why I just say I only approve a part of them, because the condition of n needs to be. Because if we do the factorization of n with n, so we have factorization with n. So we have what? We have, that's p. Normally we have p1 to the a1 times p2 to the a2 and so on times to pk to the ak. But right here the condition is a1, a2 to ak. All of them is equal to 1. So that's p1 to the 1 and then p2 to the 1 and then times point so on. And then to pk to the 1. So that's the condition of n. So right here, that means b to the phi of p1, and this part is congruent to 1 mod p1 because the whole problem, first b and n need to be co-prime. So if b and n are co-prime, so of course b and every factor of n are co-prime. So b is co-prime with p1. So this part is congruent to 1 mod p1. And then this part to phi of p2. So what happened here? Because, of course, Fermat's little theorem is, of course, I'll talk about later here. So right here, and b in this part, b to the 5 p1, it is just a lot of b times together. So that means this one is still just, and of course, and b is also co-prime with p2. So that's why this part this whole part is what is co-prime with what? Is congruent to 1 mod p2 and so on to the whole part to the phi of pk. So that's part of the whole part, and the whole part right here, it is congruent to what? And the whole part right here is not congruent. The whole part right here is just a b times a lot of b times together. A lot of b times together. So that's it. So what we do here now? So b is congruent with b is co-prime with pn. So this whole thing, that means b to the phi of n is what is congruent 1 mod pk, and exponential right here, they have the chance to let themselves move to the last exponential's place. So that's why b to the 5n is congruent 1 mod P1 mod P2 mod P3 and so on to mod Pk. So of course b to the 5n is congruent to 1 mod n. That's why. So I think I can prove it, but I only prove a part of our certain theorem, right? Okay, great. So now let's gonna prove. So then I'm gonna start. Of course, in my experiment of proving the number theories problem, I sometimes when you can't solve some problems and you should dare to prove the stronger theorem. Right here is Fermat's little theorem's stronger theorem, and this is all a certain theorem. So you should dare to prove that the stronger theorem is all a certain theorem.